Let's start our today's lecture. In our previous lecture, we covered sequential logic, SR latch, SR flip-flop. In our today's lecture, we'll start with JK flip-flop. We'll start designing our JK flip-flop and we'll start from scratch of SR flip-flop. This is the logic diagram of SR flip-flop, which is designed using NAND gates. We have two NAND gates here. This is the function table of this SR flip-flop. From this table, when we can see when S prime equal to 0 and R prime equal to 1. S prime equal to 0 means S equal to 1, R equal to 0, which means the circuit is set. The output will be set. Set output means Q equal to 1, Q prime will be equal to 0. When S prime equal to 1, R prime equal to 1, it means S equal to 0, R equal to 0, it will hold the previous value. So what was the previous value of Q? The previous value of Q was 1, so it's holding that memory, and the previous value of Q prime was 0, and the next value is also 0. It's holding the previous value. Next, when S prime equal to 1, R prime equal to 0, it means S equal to 0, R equal to 1. R equal to 1 means the output will be reset. So the value of Q will be 0. Reset means 0. So if the value of Q is equal to 0, the value of Q prime will be equal to 1. For S prime equal to 1, R prime equal to 1, that means S equal to 0, R equal to 0, the output will hold the previous value. What was the previous value? The previous value of Q was 0, so it's holding the previous value. The previous value of Q prime was 1, it's holding the previous value. For 0, 0 input, we know the output is invalid. Next, with this SR flip-flop, what we did, we added two more extra NAND gates and one extra feature, that is the clock pulse. What is clock pulse? The detail about clock pulse was described in the previous lecture. We have S input here, set input and reset input. This is the function table for the flip-flop with clock pulse input. When clock pulse of this flip-flop is 0, that means one of the input of this NAND gate and one of the input of this NAND gate is 0. So we do not care about what is the input for S and R, as one of the input of both NAND gate is 0. The definite output here, U and V, will be 1 and 1. From our previous slide, we know that when we have 1, 1 here, it will hold the previous value. That means it will act as memory. So when clock pulse equal to 0, we do not care about the input in S and R, as one of the input of these both NAND gate is 0. The output Q will hold the previous value. But when clock pulse value is 1, that means one of the input of this NAND gate and this NAND gate is 1. Now we need to see what is the value of S and R. So what is the value of S? S equal to 1 and R equal to 0. We are considering this S equal to 1, R equal to 0. So S equal to 1 will give us S1 and clock pulse 1 will give us U equal to 0 and V equal to 1. So U equal to 0, V equal to 1 means circuit is set. Set means Q equal to 1 and Q prime is 0. When clock pulse equal to 1 but S equal to 0, R equal to 0, it will hold the previous value. When clock pulse equal to 1, S equal to 0, R equal to 1, R equal to 1 means the output is reset. So reset output means the Q value is 0 and Q prime is eventually 1. When clock pulse equal to 1, S equal to 0, R equal to 0, it will hold the previous value. When clock pulse equal to 1, S equal to 1, R equal to 1, the output is invalid. The detail was described in our previous lecture. Next, we added a pulse transition detector with this clock pulse, and this flip-flop becomes edge-triggered flip-flop. Edge-triggered flip-flop. That means when clock pulse triggers, clock pulse goes from 0 to 1. This is positive edge triggering, and when clock pulse goes from 1 to 0, that is negative edge triggering. We are considering positive edge triggering here. So when clock pulse goes from 0 to 1, at that moment the output state is changed. The function table is same as previous case except this clock pulse triggering case. In previous case, clock pulse, if the clock pulse value is 1, then output state changes, but here when the clock pulse triggers, the output state changes. Now this is the complete logic diagram of SR flip-flop. From here we'll design our JK flip-flop. In order to design JK flip-flop, we need to take two feedback from the output side. One feedback is taken from Q prime to the input S side. Another feedback is taken from Q to the input R side. Here two extra features are added. Two feedbacks are taken from the output side. One is taken from Q prime, another is taken from Q. With this feedback, this complete flip-flop is renamed as JK flip-flop. So instead of writing S, we'll write J here. Instead of writing R, we'll write K here. This J is analogous to our set case, and this K is analogous to our reset case. So this is the complete logic diagram of JK flip-flop. Now let me describe the operating principle of this JK flip-flop. Let's start with clock pulse value is equal to 0. So when clock pulse value is equal to 0, that means this 0 will appear here because there is no transition. So one of the inputs of this NAND gate and this NAND gate is 0. So we don't have to bother about J and K input and these feedback inputs, because as one of the input of this NAND gate is 0 and this NAND gate is 0, so we don't have to bother about J and K input. The definite value of U and V is 1 and 1. Now look at this portion. This portion is nothing but our SR latch, and we know the operation of our SR latch. The value of U is 1 and V is 1. So if we have 1 1 here, the output will hold the previous value. So when clock pulse equal to 0, whatever the value we have in J input and K input, the output will be the previous output. This is the function table. In function table, you can see when clock pulse equal to 0, whatever the value of J and K are, the output will be the memory. Memory means it will hold the previous value. Now let's consider for the clock pulse value equal to 1. Clock pulse 1 means when clock pulse goes from 0 to 1. So when clock pulse goes from 0 to 1, at that moment this input will be 1 and 1. So one of the input means clock pulse input for both these NAND gates are 1. So we need to know what is the value of J and K and these outputs values in order to find the next output. So first of all, let's consider J equal to 1, K equal to 0. So as one of the input K has become 0, the output of this NAND gate will be definitely 1. We don't have to bother about this feedback. So as we know, the K input is 0, the output will be 1. But here we have clock pulse equal to 1, J equal to 1. In order to know the value of U, we need to know what is the value of Q prime that is coming as feedback. But for the time being, we do not know what is the previous value of Q prime. But what we know, the previous value of Q prime can be either 0 or 1. So we'll take both the cases. First of all, case 1. Case 1, Q prime equal to 0 and Q equal to 1. We are considering Q prime equal to 0 and Q equal to 1. As Q prime is equal to 0, this 0 will appear as input of this NAND gate. So we have clock pulse equal to 1, J equal to 1, but this feedback is equal to 0, which is coming from the previous value of Q prime. So what will be the value of u here? As one of the input is 0 here, so the value of u will be 1. So when we have u equal to 1, v equal to 1, this portion which is acting as SR latch, this portion, and here we are getting 1 1. For 1 1 input, the output will hold the previous value. So for case 1, when we have q equal to 1 and q prime equal to 0, the next output will also be q equal to 1, q prime will be 0. I am not writing the value here because we'll see other case. Then we'll finalize what should be put here. Now for the same set of input, if we consider another case, that means case 2, where the value of q prime was 1, we consider the value of q prime is 1, that means q equal to 0. So this q prime value is 1 and q equal to 0. In that case, we have previous value q equal to 0, q prime equal to 1. This 1 is appearing here. When this 1 is appearing here, so we have j equal to 1, clock pulse equal to 1, and feedback is 1. So the value of u will be 0. The value of u will be 0. For 0 and 1 input, the circuit is set. So for set output, this output will be converted to 1 and 0, because whenever 0 and 1 will appear here, the output will be set. Set means q equal to 1, q prime will be 0. So for both the cases, we are getting q equal to 1 and q prime equal to 0 for j equal to 1 and k equal to 0. So I can write q equal to, for j equal to 1, k equal to 0, when clock was triggered, the output q equal to 1 and q prime equal to 0, which is considered as set case. So this j is analogous to our set case, k is analogous to our reset case. So when j equal to 1, the circuit is set. When we will see what will happen when k equal to 1. So this is the set case. Now let's see when clock pulse equal to 1, j equal to 0, k equal to 0. What will happen? J equal to 0, k equal to 0. We don't have to bother about other inputs, as one of the input of this NAND gate and this NAND gate is 0. So the value of u will be equal to 1 and v will be equal to 1. As we have u equal to 1 and v equal to 1, the output of this portion, that means SR latch, output of this portion which is considered as SR latch, will be the previous value. That means it will hold the previous value. So for clock pulse triggering, what was my previous value? Previous value is 1 0. It's not the value is not 1 0 because it's set. Rather, my previous value was 1 and 0. That's why the next value will also be 1 and 0. So for 0 0 input, it will hold the previous value. What was the previous value? The previous value of it was 1, so it's continuing. The previous value of q prime was 0, so it's continuing. So this will act as memory. Again, when j equal to 0 and k equal to 1, as one of the input of upper NAND gate is 0, we know the definite value of u is equal to 1. But here clock pulse equal to 1, k equal to 1. So in order to know the value of v, we need to know what was the previous value of q. We do not know what was the previous value of q. So let's consider two cases. Case number 1, q equal to 0, q prime equal to 1. That means first of all we'll consider q equal to 0, q prime equal to 1. This 0 will appear here, as one of the input of this NAND gate is 0. The definite output of v is 1. So we are getting v equal to 1, u equal to 1. So for this small portion, SR flip-flop, if you consider this as SR flip-flop, the inputs are 1 1. We know for the inputs having 1 1 values, the output will hold the previous value. Here I am not going to put the output values in this table because we need to check another case as well. Now let us see another case where we will consider q equal to 1 and q prime equal to 0, the previous case. That means we will take q equal to 1, the previous output of q is equal to 1 and q prime is equal to 0. So as j equal to 0, we can say the definite output of u is 1, right? But here k equal to 1, clock pulse equal to 1. Now we need to see what was the previous output. The previous output will come from q. Q is 1, so this 1 will appear here. So we have 1 1 1, so the output of v will be 0, so it's 0. So whenever we have 1 and 0 in this SR flip-flop, u equal to 1 and v equal to 0, the output is reset. Reset means q will be 0 and q prime will be 1. Hence, for both the cases, when j equal to 0, k equal to 1, we are getting output q equal to 0, q prime equal to 1. That means k equal to 1 means reset. So output will be reset. Reset means output will be 0. Now we can put the values on function table, because for both the cases we have found the same thing, that is for 0 1 input the output will be reset. Next, after this state, if we again give j equal to 0, k equal to 0, that means 0 0, so the value of u will be 1, v will be 1. As we have 1 1 here, the output of this SR latch will hold the previous value. What was the previous value? We know the previous, we consider this as previous value, q equal to 0, q prime equal to 1. So the next value will also be q equal to 0, q prime will be 1. So for 0 0 input, the output will be the previous output. It will act as memory. Now if you can recall, we know for our SR flip-flop case, when s equal to 1, r equal to 1, set equal to 1 and reset equal to 1, the output was invalid. I believe all of you can recall. One of the unique feature of JK flip-flop is that when we have j equal to 1, k equal to 1, output is not invalid. So we'll see what will happen when you provide j equal to 1 and k equal to 1. Let's see the operation. We are giving j equal to 1 and k equal to 1. As we have j equal to 1 and k equal to 1, clock pulse is equal to 1. So this output u and v depends on the feedback from q prime and q. Feedback will come from the previous value of q and q prime. So we need to take two cases. First of all, we'll take the previous value of q and q prime. We are taking q equal to 0 and q prime equal to 1. So q equal to 0 and q prime equal to 1. This 0 value, q equal to 0 value, will appear at the k side, and this 1 value, that means q prime equal to 1, will appear at the j side. At k side, we have feedback from q. This feedback will appear here. The value of q is 0. So this 0 will appear here. So we have clock pulse equal to 1, k equal to 1, but feedback is 0. So the value of v will be 1. At j side, we have j equal to 1, clock pulse equal to 1, and this feedback will appear at this gate. So this value is 1. So the output, again, this q prime feedback will appear here. Here we have clock pulse equal to 1, j equal to 1, and one feedback that is coming from q prime. The value of q prime we have taken as 1. So this 3 1 will give us the value of u is equal to 0. So we have 0 here, 1 here. So if we have 0 and in the u side and 1 in the v side, the output of this SR latch will be set. Set means q will be 1, Q prime will be 0. So if our previous condition of Q is 0, it becomes 1 for this 1 1 case. Now we'll see the next case, case number 2. For case number 2, again we are taking k equal to 1, j equal to 1, both are 1. So in case 2, we'll consider q equal to 1, q prime equal to 0, opposite of the previous case. So we have q equal to 1 and q prime equal to 0. So this 1 value will appear at the k side. So this 1 value will appear at the k side. We have feedback equal to 1, k equal to 1, and this clock pulse equal to 1. Eventually the output for V will be equal to 0. Again, this q prime feedback will appear at the j side. So we have j equal to 1, clock pulse equal to 1, but q prime is equal to 0. So the value of u will be 1. Again, for this SR flip-flop, we have u equal to 1, v equal to 0. That means the output will be reset. Reset means the key value of q will be 0, q prime equal to 1. Let me show you two cases, putting them side by side. In case 1, when the previous output was q 0, that means q equal to 0, and obviously q prime will be 1. By giving 1 1 input and clock pulse, this 0 becomes 1, 1 becomes 0. Again, for case 2, where the previous case was 1 0, by giving 1 1 as jk input, this 1 becomes 0 and 0 becomes 1. So what's happening here? By giving 1 1 input, the outputs are being toggled. The output, if output is 0, then it becomes 1. If output is 1, it becomes 0. So output is inverted or toggled. That's why this mode is named as toggle mode. So from the function table, if the previous output is 0 and 1, 0 q equal to 0 and q prime equal to 1, then by giving 1 1 input, we'll get inverted version of the previous output. 0 will become 1, 1 will become 0. Again, if the previous output was 1 0, then by giving 1 1 input, this 1 will be inverted to 0 and 0 will be inverted to 1. So these outputs are toggled output of the previous value. If you observe the characteristics table of JK flip-flop, we can see when clock pulse equal to 0, we do not care about J input and K input. The output will be always the previous output. It will hold the memory. If I think that QT plus 1 is my present output, then QT will be my previous output. But when clock pulse triggers, for 0 0 input, it will hold the previous data. For 0 1 input, 0 means j equal to 0, k equal to 1, k equal to 1 means it's in reset condition, so the output will be reset. That means output will be 0. When j equal to 1 and k equal to 0, it's set input, so the output will be set. Set means 1. When we have 1 1 input, the output will be the toggle value of the previous value. The previous value is qt, the next value will be q prime t. That means output will be toggled. Here the graphic symbol for JK flip-flop is shown here. We can see J input is here, K input is here, Q output and Q prime output. There is a clock pulse input. This triangular notch signifies the edge triggering case, and this is positive edge triggered flip-flop as we do not have any bubble here. What we have inside this box? Inside this box we have this logic diagram. This complete logic diagram is inside this box. In this slide we can see graphic symbol for positive edge triggered flip-flop and graphic symbol for negative edge triggered JK flip-flop. In negative edge triggered JK flip-flop, we have a bubble at the input side of the clock pulse. Things will be more clear if we draw a timeline diagram for these types of JK flip-flops. Let's draw the output timeline diagram for this JK flip-flop, where we have clock pulse input is this, J input is this, and K input is this. We have time at x-axis and we have the values in the y-axis. From the graphic symbol of this JK flip-flop, we can understand this is negative edge triggered JK flip-flop. So all the output states will be changed when clock pulse goes from 1 to 0. At this negative edge, when clock pulse goes from 1 to 0. Hence, we will draw lines at the negative edge of the clock pulses. So here are the lines which is drawn at the negative edge of the clock pulses. For the time being, let us assume the initial value of Q is 0. It will start from 0 value. Later on, I'll show you the modified version of JK flip-flop where we'll set the initial values. Now, first state change will occur here. So, from here to here, the output will hold the previous value. There will be no change. Now, at this transition period, that means when clock pulse goes from 1 to 0, the value of J is 1, the value of K is 0. So, this is the set condition. So, output will be set, output value will go to 1. This 1 value will continue up to this timeline. Here, when clock pulse goes from 1 to 0, the value of J is 0, value of K is 1. When we have K is 1, K is analogous to our reset case. So, and this reset value is 1. So, the output will be reset, that means 0. It will go back to 0 position. And this value will continue up to this line. There will be no change as there is no negative edge triggering in between. Now, at this triggering point, we have J equal to 1 and K equal to 1. When we have J equal to 1 and K equal to 1, the output will be the toggled value of the previous output. What was our previous output? We can see our previous output is 0. So, for 1 input, the output will be the inverted value of the previous output. So, inverted value of 0 is 1. So, we can see it goes from 0 to 1. Now, this line will continue from here to next negative edge triggered line. At this triggering point, we can see J equal to 1 and K equal to 1. Again, for J equal to 1 and K equal to 1, the output will be the toggled value of the previous value. What was my previous value? The previous value was 1. So, the toggled value of 1 is 0. So, it will go back to 0. And it will continue from here up to next negative edge triggering line. Here we can see when negative edge triggering occurs, we have J equal to 1 and K equal to 0. J equal to 1 means set. So again, it will go to the set position. In this way, I hope you will be able to draw the output timeline diagram for any sets of inputs. Next, we will start a new type of flip-flop, that is T flip-flop. T stands for toggle. It means it's toggle flip-flop. T flip-flop is nothing but a modified version of JK flip-flop. The inputs of JK flip-flops are shorted together. So, here we have only one input and one clock pulse. When we give T equal to 0, both J and K get 0. When we give T equal to 1, both J and K get 1. And this is the graphical symbol of T flip-flop. Inside this box, we have this red zone portion. And we have one input, T input, clock pulse input, Q output, and Q prime output. The operation of T flip-flop is very simple. If you understood JK flip-flop, then the operation of T flip-flop is very simple. Here we can see the characteristics table for T flip-flop. When clock pulse equal to 0, no matter what the value of T is, it will always hold the previous value, that means memory. But when clock pulse triggers, if T equal to 0, it will hold the previous memory. T equal to 0 means inside this box we have JK flip-flop. T equal to 0 means J equal to 0, K equal to 0. J equal to 0 and K equal to 0 will hold the previous value. So T equal to 0, it will hold the previous value. When T equal to 1 means J equal to 1, K equal to 1. When we have J equal to 1 and K equal to 1, it will toggle the previous output. So when we have T equal to 1, it will toggle the previous output. Let us draw a timeline diagram for T flip-flop case. We will draw a timeline diagram for this T input case. From this graphical symbol, we can see that this T flip-flop is positive age triggered flip-flop. Positive age means when clock pulse goes from 0 to 1. Let us mark the positive edges lines of clock pulses. This is one line, another line, all the positive edge lines. The states will be changed here in this line. So at the very initial moment, we are considering the output is to be 0. So it will hold the previous data. When clock pulse triggers, it will see the input T. What is the value of input T when clock pulse triggers? The input T is equal to 0 at this line. When it is 0, it will hold the previous data. What was the previous data? Previous data was 0. So it will hold the previous data up to this time. At this triggering point, again, what is the value of T here? The value of T is 0 here. So it will hold the previous data up to this time. When clock pulse triggers for the third time, we see we have T equal to 1. T equal to 1 will toggle the previous output. The previous output was 0, so it will come to 1 position and it will continue up to next triggering point. When clock pulse triggers again, we see here we have T equal to 0. T equal to 0 means it will hold the previous data. What was the previous data? In this case, the previous data was 1. So it will continue this value. At the next triggering point, we see T equal to 1. So when T is equal to 1, it will toggle the previous value. What is the previous value? Previous value in this case is 1. So 1 will come back to 0 and it will continue. I hope all of you understood. Next, we will design D flip-flop. D flip-flop is the modified version of SR flip-flop. Here, S input is shorted with D input and R input is connected through a NOT gate with D input. So one input, whenever D is 0, S will directly get 0, but R will get the inverted input of D. So if we take this portion as in one box, this circuit becomes like this. We have D flip-flop. Inside this box, we have the area covered by these red lines. The operating principle of D flip-flop is very simple. If you understood the operating principle of SR flip-flop, then it becomes very easier to understand the operating principle of D flip-flop. Whenever we give D equal to 0, inside this box there is an SR flip-flop. S will get 0, R will get 1. Whenever we'll give D equal to 1, S will get 1, R will get 0. Let's see the characteristics table for D flip-flop. This is the characteristics table for D flip-flop. When clock pulse is equal to 0, whatever the value of D is, the output will be the previous output. That means it will hold the previous value. It will act as memory. But when clock pulse triggers, if D equal to 0, after this triggering, this 0 will be transferred to the output side. When D equal to 1, after the clock pulse triggering, this 1 will be transferred to the output side. That means here the data is transferred from input to output with the clock pulse triggering. You may try the timeline diagram for D flip-flop. For inputs and clock pulse, you may use the one that was shown for the T flip-flop case. So far we have covered 4 types of flip-flop: SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. These are the graphical symbol for SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. All of them are having positive edge triggering. The negative edge triggered flip-flop will have a bubble at the input of each clock pulse section. Now let me summarize output for different inputs for each flip-flop case. For SR flip-flop, if S equal to 1, R equal to 0, S equal to 1 means set equal to 1, so the output will be set. S equal to 1, R equal to 0, the output will be set, that means Q will be 1. S equal to 0, R equal to 1, output will be reset, Q will be equal to 0. S equal to 0, R equal to 0, output will be the same as previous output. And for S equal to 1, R equal to 1, the output is invalid. For JK flip-flop, if J equal to 1, K equal to 0, J is analogous to set case. So if J equal to 1, that means the output will be set, that Q will be equal to 0. K equal to 1, J equal to 0, output will be 0, reset case. J equal to 0, K equal to 0, the output will hold the previous output. J equal to 1, K equal to 1, output will toggle the previous output. For T flip-flop, when T equal to 0, it will hold the previous output. When T equal to 1, it will toggle the previous output. For D flip-flop, when D equal to 0, it will transfer the 0 output. When D equal to 1, it will transfer the 1 output at each clock pulse triggering. I hope all of you understood the basic operations of these flip-flops. Well, that's all for today. Feel free to contact me if you have any question.